Have you ever run across a circuit like this and wondered what and why? Well, that's the purpose of this tape, to teach you about basic digital logic. The objective of the material you're about to view is to teach you enough about the behavior of the logic elements that are covered in each segment to allow you to predict their outputs when you know their inputs. In each segment, we'll describe the behavior of one or two logic devices and give you examples of their behavior. Then we'll give you a chance to stop the tape and work some problems to test your understanding of the material you've covered. We will start with AND gates and OR gates. But first, we should talk a little about basic digital logic. In binary digital logic, we're dealing with only two possible states. We may call the two states high and low, ones and zeros, true and false, even John and Mary. In fact, we may call them by any two different names we wish. In this discussion, we're going to use 1 and 0 for our two possible logic states. With these ones and zeros, we can make certain logic decisions. If one input to a logic circuit is a 1 and another input is 0, that will result in the output being either a logical 1 or 0. We can represent these logic conditions with symbols. This first symbol is the symbol for an AND gate. Notice that this AND gate has 3 inputs. An AND gate may have 2 or more inputs. It may have only 2, or it might possibly have thousands of inputs. AND gates usually have only one output. If we have more inputs than can be drawn on the symbol, we change the AND gate symbol. We use this symbol. Notice we've drawn some ears on the AND gate. These can be extended up and down as far as necessary to make room for the inputs and the AND gate. These are all symbols for AND gates. Now, let's talk about what AND gates do. The behavior of an AND gate is fairly simple to describe, and this description is something that you should commit to memory if you're going to be working with digital logic. An AND gate will have a 1 output only when all its inputs are 1s. Remember, we said there are only 2 possible states in digital logic. If any of the inputs are not 1, then the output of the AND gate can't be a 1, so it must be 0. That's the only other possible state in a binary system. So, if you can just remember that when all inputs are 1s, the output will be a 1, then you understand the behavior of AND gates. Now let's look at a few examples. Notice that on the inputs we have 1s on the top 2 inputs and a 0 on the bottom input. Remember that an AND gate must have 1s on all inputs to have a 1 at the output. We haven't met the requirements of that statement, therefore the output must be 0, as we have shown here. Now let's try another one. This is a 4-input AND gate. This time all the inputs are zeros. Again, the inputs do not meet our requirement for all 1s on the input to get a 1 at the output. Naturally, if the output isn't a 1, it has to be a 0. If all the inputs had been 1s, we would have a 1 on the output. This is the behavior of AND gates as we usually see them. Here is a symbol that is slightly different than the ones we saw a moment ago. This one is a wired AND gate. Notice that on this symbol, the left 2 inputs come into the symbol, and there's a connection to the wire that goes to the output. In other words, the inputs and output are all electrically tied together. This is a wired AND gate. It's nothing more than 3 pieces of wire tied together. The thing that makes this wire perform an AND function is the driving circuitry on the left. Depending on the type of driving circuitry, this may be an AND gate or an OR gate, which we'll see later. Again, and this is very important, the type of circuitry that is driving this wired junction is what makes the wiring perform as an AND gate. You must have the driving circuitry trying to pull both inputs toward a 1 state in order to have a 1 at the output. The behavior is almost identical to the conventional AND gate. The circuits driving the wired AND gate must both be trying to pull the wires to a 1 state in order to output a 1. If either circuit driving the gate is trying to pull an input toward a logic 0, the output of the AND gate will be a 0 because the inputs do not meet the requirements necessary for a 1 output. All inputs must be 1s in order to have a 1 output. Now let's take a look at the digital logic OR gate. This is the symbol for an OR gate. On this symbol, there are 3 inputs on the left edge of the device. The OR gate has a minimum of 2 inputs, but the digital logic OR gate may have as many inputs as the designer can squeeze in. 2, 3, or 4 input OR gates are not at all uncommon. If we have more inputs on the OR gate symbol than we have room to draw, we use a symbol like this. You can see there's quite a similarity between this and the AND gate as far as the technique that's used to symbolize the increased number of inputs. We have ears drawn on the OR gate to accommodate the extra inputs. The artist may add more ears if there are more inputs. These curved lines typically have 2 or 3 inputs on each curve, and if we need more inputs, we put another set of curved lines above and below in order to accommodate the additional inputs. What does the OR gate do? As with the AND gate, there is one statement that completely describes the behavior of the digital logic OR gate, and this is the second one you should memorize. That statement is, if any one or more inputs are a 1, the output will be a 1. Let's do what we did with the AND gate. We'll put some examples on the screen and analyze them. See if you can determine the outputs using this rule. If any one or more inputs are a 1, the output will be a 1. This is a 2-input OR gate, and on the left edge of the OR gate, we have all 1s applied. We said if any one or more inputs are a 1, the output will be a 1. In this case, all the inputs are 1s, so the output must be a 1. Let's take one more example. Let's put a 1 and a 0 on the input to the OR gate. Here again our statement was that if any one or more input is a 1, the output will be a 1. Well, obviously we have a 1 input, so the output must be a 1. One more possible condition now. Let's apply all zeros to the input. We said that 1 or more inputs must be a 1 to have a 1 output. This example doesn't meet that condition, so the output is a 0. Now let's take a look at another symbol for an OR gate. This is the symbol for a wired OR gate. Notice that we have only 3 wires, just like we had with the wired AND gates. The first question that usually arises is, how is the wired AND different than the wired OR? They are both made of conductors, and again the answer is the driving circuitry. If we use a pair of emitter-follower NPN transistors and tie the 2 emitters together at the output, we would find that this circuit would perform the logic OR function. If the driving circuit tries to force a 1 on either or both inputs, the output will be a 1. Again, it is very important to note that when 2 wires are connected like this and used to perform a logic function, the driving circuitry is what determines whether the function is a logic AND or a logic OR. Let's take a look at one other logic device. There are 3 symbols for this device. Any binary logic level can be converted to the opposite state with this device called an inverter. These symbols are all used to symbolize inversion. We can apply a logic level at the input of any one of these symbols, and whatever logic level we apply will cause the opposite logic level at the output of the symbol. For example, if we apply a 1 to the left end of any of these symbols, then the output on the right end will be a 0. All 3 symbols represent a logic state inversion. The top symbol is probably the most commonly used symbol for an inverter, and this symbol is used when the inverter is not an integral part of a logic gate. If the logic gate has an inverter as an integral part of the circuitry, the symbol that is used will be the bottom symbol. This symbol is usually drawn as part of the logic gate. In fact, the circle is almost never used alone to symbolize inversion. It's invariably drawn as a part of a logic gate or flip-flop. The inverter is usually drawn like one of these 2 symbols unless it's part of a logic gate. Now, let's summarize what we've talked about. With the digital logic AND gate, all inputs must be 1s to have a 1 output. With digital logic OR gates, one or more inputs must be a 1 to have a 1 output. The logic inverter output will always be the opposite of the input. This completes this section. Now stop the tape and do the parts of the quiz on AND gates, OR gates, and inverters. Our next subjects are NAND gates and NOR gates. This is the symbol for a digital logic NAND gate. Notice that it has an invert symbol on the output. The digital logic NAND gate is derived from a digital logic AND gate with an inverter following the AND gate. Here you see a symbol of an AND gate followed by an inverter. This circuit performs exactly the same function as a NAND gate. With the AND gates that we talked about previously, if the AND gate has all 1 inputs, the AND gate output will be a 1. The output of this AND gate goes into the inverter. The output from the inverter will be the opposite of whatever its input is. Now watch the behavior of this circuit. Let's put 3 1s on the input of the AND gate. If we have 3 1s, that will give us a 1 at the output of the AND gate. The 1 will cause a 0 at the inverter output. This is exactly the same behavior that we would have with a digital logic NAND gate. Let's look at a slightly different version of this circuit. Let's just do away with the triangle. Now, if we slide the circle over against the AND gate, we have something that looks like this. Of course, this is the NAND gate symbol. The circuit still behaves the same because we still have the inversion. To analyze NAND gates, we can take the inputs and use those to determine what the output will be from the AND portion. Then, take that output and run it through the inverter and determine the output from the inverter. That's a 2-step analysis of the behavior of a NAND gate. This 2-step method of analyzing digital logic NAND gate is preferable to memorizing an axiom such as we did with the AND gate. This is probably the easiest method of analyzing digital logic NAND gates. Now, let's take a look at digital logic NOR gates. This is a symbol for a NOR gate. Notice that it's very similar to the OR gate, except that it has the circle on the output. We analyzed the NOR gate in very much the same way we did the NAND gate. We mentally move the circle out of the way and apply some inputs to the OR portion of the gate. In this case, let's take 2 0 levels. If we have 2 0 levels at the input to an OR gate, we will have a 0 at the output of the OR gate. If we have a 0 there and we pass that through the invert symbol, that will give us a 1 at the output. This method of analysis will apply to all NOR gates. We can treat the NOR gate as an OR gate followed by an inverter. Let's take a look at another picture. Here we have a symbol which may appear to be a variation of the NAND gate. This symbol should not be referred to as a NAND gate because it performs a different function. Notice that the invert symbols are on the input rather than on the output. This device should be referred to as an inverting input AND gate, not as a NAND gate. Here's another commonly used symbol. This is an inverting input OR gate. This symbol should not be confused with a NOR gate. It performs an entirely different function. Analysis of these 2 gates follows the same general procedure that we used in the previous example. We apply an input, we take that input and see what effect the inverters may have on that input. Then the inverter outputs are used to determine the output of the OR portion of the gate. Here's an example. We'll apply a 1 and a 0 to this inverting input OR gate. So now you can see that NAND gates, NOR gates, OR gates, and the like have similarities in their behavior. The only big difference is the fact that we have combined inverters with either AND gates or OR gates. The analysis is just a simple process of taking care of the inversion and taking care of the logic function in separate steps. If you have an inversion, determine what the effects of that are going to be. If it's followed by a logic gate, such as an AND gate or an OR gate, determine what effect that gate will have on the signal. If there is an inverter on the output of that device, determine what effect the inverter will have on the signal. In other words, break the circuit down and take the analysis one step at a time. This completes this section of the tape. Stop the tape and do the parts of the quiz on NAND gates and NOR gates. Now I would like to talk to you about the exclusive OR gates and the exclusive NOR gates. Let's start with the exclusive OR gate. The exclusive OR gate has a symbol that looks like this. Notice that the distinguishing feature of this symbol is the extra bar at the left edge of the symbol that looks like a conventional OR gate. The behavior of the exclusive OR gate is such that when the inputs to the exclusive OR gate are different, the output will be a logic 1. Under all other conditions, the output will be 0. This behavior is similar to the conventional OR gate, with the exception of the condition where both inputs are a 1. Let's run through a few of the possible input conditions and see the behavior of the exclusive OR gate. If we have 2 zeros at the input to the exclusive OR gate, the exclusive OR gate behaves just like the conventional OR gate. The inputs are not different, so the output should be a 0. With 2 zeros at the input like this, that will result in a 0 at the output like this. Now let's apply a 0 at one input and a 1 at the other input. We'll put a 1 at the top and a 0 at the bottom. Remember that if the inputs are different, the output will be a 1. Well, obviously, we have different inputs in this case, so the output will be a 1. The same thing would happen if we had a 0 input at the top and a 1 input at the bottom, so we won't go into that one. Now let's look at what happens if we have 1s at both the inputs to the exclusive OR gate. Remember our statement, the inputs have to be different from each other in order to have a 1 output. The 2 1s at the input don't meet those requirements, so we have a 0 at the output. Next, let's look at the exclusive NOR gate. This gate behaves the same way except for the inverter on the output. We can look at this inverter just as we did with the conventional NOR gate. We can slide the inverter over to the right and get it out of the way and then apply our conditions at the input. Determine what the output would be by using our previous technique for exclusive OR gates. Run that output through the inverter, and the output shown on the inverter should tell us what the output of the exclusive NOR gate is. The exclusive NOR gate is sometimes referred to as a coincidence gate. The reason for this is because the inputs must be the same, or coincidence, to have a 1 output. Now you're ready to stop the tape and do the quiz questions on exclusive OR gates. Next, I'd like to talk to you about positive and negative logic. We talked about using 1s and 0s as the 2 logic conditions for our logic discussions. And as I'm sure you're aware, in most of the logic diagrams we deal with in the real world, we work with voltage levels rather than 1s and 0s. We use voltage to represent logic 1s and 0s. For example, we might use a plus 2 volt level to represent a logic 1, and a minus 1 volt level to represent a logic 0. Now we have to relate these voltage levels to the 1s and 0s that we use when we discuss digital logic. Let's start out by making this statement. When you work with a logic diagram, you should first determine the circuit behavior using 1s and 0s. Once you've done this, you can plug in the appropriate voltages in place of the 1s and 0s. To do this, of course, you must have a definition of what a logic 1 represents in terms of voltage and what a logic 0 represents in terms of voltage. For example, if we arbitrarily define a 1 as a voltage that is greater than plus 0.5 volts and a logic 0 as a voltage that is less than 0 volts, then we have a definition. This definition might apply to any of the logic gates that we've talked about in the past. If we do make a definition like this, where the most positive or the least negative voltage represents a 1 level, this logic system is said to be a positive logic system, or a positive true logic system. Now, let's take another condition where we have a relatively low voltage or even a negative voltage as our logic 1 level, and something less negative or more positive to represent the 0 level. We'll show this on this chart. Notice that the 1 level is closest to the negative end of our graph. When the logic 1 is more negative than the logic 0 level, we say that we have a negative logic system. The terms positive logic and negative logic refer to the relative voltage level of the logic 1 with respect to the logic 0 voltage level. To summarize, if we wish to know whether a system uses positive or negative logic, all we need do is note the polarity of the 1 level with respect to the 0 level. Not with respect to ground, by the way. If the 1 level is positive with respect to the logic 0 level, regardless of the voltages with respect to ground, then the system is said to be a positive logic system. By the same token, if the 1 level is negative with respect to the logic 0 level, the system is a negative logic system. The circuits shown in the remainder of the course all use positive logic, but there are many older schematics that were drawn using negative logic, so you should be aware of the existence of the two forms. In circuits where the logic levels are referred to as true or false, a true and a logic 1 represents the same thing, and of course a false is the same as a 0. The logic states called high and low refer to voltage levels, and it's necessary to know whether you're dealing with positive or negative logic in order to relate highs and lows to trues and falses, or to ones and zeros. We're using positive logic in all the following material unless otherwise noted, so any references to a logic high is the same as a logic 1 or a true. This completes this section. When you've completed the part of the quiz on positive and negative logic, you're ready to view the next segment.